Now we introduce the more general description of diffraction developed by Max von Laue. Instead of treating the crystal as reflecting lattice planes, the Laue approach views the crystal as a collection of microscopic objects or scattering centers. They can be atoms, ions, or groups of atoms, etc. Each microscopic object in the crystal acts like a small source that re-radiates the incident wave in all directions. This leads to the more fundamental picture shown here. So we have the incident wave vector k and the scattered wave vectors, for example, k prime, k double prime, and k triple prime, and so on and so forth. Unlike the Bragg picture, we do not assume specular reflection. So the reflected angle of the reflected X-ray beam is not necessarily to be equal to the incident angle. Instead, we simply consider interference among waves scattered by all microscopic objects in the lattice. So the von Laue approach differs from the Bragg approach in that no particular sanctioning of the crystal into lattice planes is performed, and no assumption of specular reflection is imposed. This in reality comes from the fact that microscopic objects can scatter the incident beams or waves in all directions. Then by analyzing the interference conditions, we can determine when constructive interference occurs. The remarkable result is that diffraction occurs when the change in wave vector matches a reciprocal lattice vector. This is the essence of the Laue diffraction condition. To derive the diffraction condition more formally, we begin by examining two scattering centers, or scatterers, separated by a displacement vector d. Here we have an incident plane wave with a wave vector k coming in this direction, and it is scattered by the two scatterers as shown. Since the incident wave is scattered in all directions, it is possible to pick up the scattered waves with the same wave vector k prime originating from the two scatterers. As the two scatterers are located at different positions, the scattered waves acquire a phase difference. The phase difference between two scattered waves at a given observation point depends on the path difference between the two scattered waves, which is the sum of the projections of the displacement vector d along the incoming and outgoing directions. So as seen in the figure, the path difference between the two rays or waves is given by d cosine theta plus d cosine theta prime. Each term can be further rewritten as d dot n hat and minus d dot n hat prime, where n hat and n hat prime denote the unit vectors of k and k prime respectively. And when expressed in terms of the unit vectors n hat and n hat prime, a minus sign is required because the projection of the displacement vector d onto the direction k prime, which points to the left, is in the opposite direction of k prime. So for constructive interference to occur, the path difference must be an integral multiple of one free space wavelength denoted by n lambda, where m is an integer. Multiplying both sides of this equation by 2 pi divided by lambda naught, we obtain this equation. So it is the phase condition for constructive interference. Now suppose that the scatterers lie on a Bragg lattice. In that case, the displacement vector d becomes a lattice translation vector r. As shown in the figure here, we depict two lattice translation vectors, R1 and R2, that have different directional cosines. The incident wave vector is k, and one of the scattered wave vectors originating from these two scatterers is k prime. So constructive interference of all scattered waves from the entire lattice occurs when this equation r dot k minus k prime equals 2 pi times an integer holds for all lattice translation vectors. From what we have obtained on the previous page, we know for constructive interference to occur, the inner product of the lattice translation vector and the change in the wave vector must be equal to an integral multiple of 2 pi. That mathematical expression can be written in the equivalent form shown here for all the lattice translation vectors. Comparing this condition with the definition of the reciprocal lattice, which is e to the ig dot r equals 1, where the bold capital G represents the reciprocal lattice vector, we arrive at one of the most important results in solid state physics, the Laue condition, where the reciprocal lattice vector G must be equal to the outgoing wave vector k prime minus the incoming wave vector k. It tells us that constructive interference occurs when the change in wave vector equals a reciprocal lattice vector. So please fill in the blank here. Constructive interference will occur provided that the change in wave vector is the reciprocal lattice vector. This result beautifully connects diffraction experiments with the concept of reciprocal space that we discussed earlier.